Chapter 2, Section 1, Problem 13. Show that any group of order 4 or less is abelian. We obviously need to know what a group is to do this problem. So remember, a group is a set with a defined operation star that holds these 4 axioms. So 1, closed. Given any 2 elements of the group, we can multiply them together and get back another element of the group. Associative, we can apply multiplication as shown. Remember, that doesn't mean you can swap A and B necessarily. Identity, there exists a special identity element E. So this is going to be very important for us. So there is a special, unique element in the group, which we call E, such that A star E equals E star A equals A for all A in G. And then number 4, inverse. For every A in G, there exists an element B, such that A star B equals B star A, which equals E. We're going to need that as well. And then remember, abelian means that for any 2 members of the group, we can swap them. A star B equals B star A. So you can swap the left and right hand side under multiplication. So let's go ahead and look at this. So we're looking for groups of order 1, 2, 3, and 4. So let's start with order 1. Our axiom number 3 tells us that there exists an element in the group E. If our group only has 1 element, then that element has to be E. And we know from closure that whenever you take 2 elements of the group, it has to give you back a 3rd element. So the only option for multiplication in this group is that E star E equals E. There's no other, it has to be an element of the group. There's no other way to do that. Now for a group of order 2, again, we're going to have E. E is going to be in every single group. There is that special identity element in E. And now we have a non-identity element, which I call A. This is the entire group. You have E, and you have something that's not E. Let's call it A. Now remember, when we multiply, we have to get something back in the group. What are we going to get back when we do A star E? Well, A star E, based on our axiom number 3, has to be A. And E star A has to be A. So for this group, this is exactly what we want to show. Given any 2 elements of the group, we only have 2 elements, we want to show that we can multiply them on the left and right hand side and we get back the same answer. A star E equals A, E star A equals A. That means a group of order 2 is abelian. Now let's look at order 3. So now it gets a little more complicated. Again, we have our identity element E. You're always going to have E. And now we have 2 non-identity elements. So I call them A and B. And now we need to make sure if we take any 2 of these 3 elements, so there's a few ways to do that, that we can multiply on the left and right and get back the same answer. Now, what's the part we already know? We already know from the group of 2, and we've seen this from our axiom, the identity axiom, that we know how these A and B interact with E. The identity element always interacts the same way. So these equations right here, we get for free. We know that A star E equals A for all A in the group, in this case for A and B in the group. So those elements interact in an abelian way. They commute with each other. What's left to show is that A and B commute with each other. So we still need to show that A star B equals B star A, because those are the 2 non-identity elements, right? Well, let's look at what could possibly happen. Case 1. So what happens if AB equals E? And here I'm writing the shorthand for AB. This is technically A star B. Well, if AB equals E, then we have by axiom 4 the inverse condition that's the unique inverse for A, which means we can really just call B A to the negative 1, right? So then we get AB, which equals A to the negative 1, its inverse element. Well, that equals E. But again, by the inverse condition, here on the left, we have that A star B equals B star A, right? So if you're the inverse, then we can multiply in any direction we want. And again, we're just relabeling B as A to the negative 1 for emphasis. We could have kept this as B throughout. So we have that AB equals A times its inverse, which equals E, which equals its inverse times A, but its inverse is just B, so we get, at the end of the day, AB equals BA, which is exactly what we needed to show for the group of order 3. So in this case, if AB equals E, then this group of order 3 is abelian. But we don't necessarily know that AB equals E. We need to look at the other cases. So we have case 2, and case 3 will be exactly the same. What if AB did equal A? Then what happens? Well, there's a unique element where that happens. The unique element is the identity element, okay? So if AB equals A here, well then B has to be the identity element. But we already said that B doesn't equal E. We said that was our assumption for a group of order 3. There's one identity element and there's two non-identity elements, right? By axiom number 3, there can't be two identity elements. So this is a contradiction. And the same thing happens in case number 3. If AB equals B, then A is the identity element, which is a contradiction of A not being the identity element. So we know that the only thing that's possible is case 1. So for a group of order 3, we only have case 1. There is no case 2 and case 3 to consider because we eliminated them as a possibility. Now let's look at the group of order 4. So here the same setup. We know that E is a member of the group, and now we're going to look at 3 non-identity elements, and we get these guys for free. We know how E interacts. E is always interacts in a commutative or abelian way with every element of the group. So now we're going to look at A and B. I could have also done, as an example, A and C or B and C. It doesn't matter. If we can show that 2 arbitrary elements, non-identity elements, are abelian, then that will hold for the last element of the group, which is C. So let's show that AB equals BA. So now we have 4 cases to consider. Does AB equal E, A, B, or C? Remember, because the group is closed, those are the only options. AB has to return an element of the group. There's 4 elements to the group, so let's figure out which ones of these cases are possible. In the first case, if AB equals E, well then we're back to this inverse condition. If AB equals E, then we have that B is the inverse of A, and we know that the inverse by axiom 4 interacts in an abelian way, so we get AB equals BA. Very similar to the group of order 3. Now for case 2 and 3, this is exactly what we just did, and we already eliminated this case. If AB equals A, that means that B is the identity element, but there's already a unique identity element, and we're calling that identity element E. So we don't need to worry about case 2 and 3. What about case 4? So here we're assuming that AB equals C, so we want to show that in this case, that means that BA also equals C. Because if that was the case, then A and B would interact in a commutative way. Okay. Now what happened? Now what are the possibilities for BA? Well, we know that BA certainly does not equal E. Because if BA equals E by the same argument as case 1, that would mean that AB equals E. But here we're assuming that AB equals C. So we don't need to worry about BA equaling E. That can't happen. But we also know that BA cannot equal A, right? So if BA equaled A, we have the same problem of that means that the other element is the identity element. So we can't have that either. And we also, for the same reason, can't have it equal B. By closure, AB has to equal one of these 4 things. Same thing. BA has to equal one of these 4 things. So BA has to equal A or B or C or E. And we just showed that it definitely cannot equal E, A, or B. Therefore, BA equals C. Thanks for watching this video. I hope you enjoyed it. Make sure to subscribe so you don't miss out on future videos. And if you have a question about this problem or if you'd like to request a solution to a different problem you're working on, let me know in a comment below.